Michelson-Morley experiments of 1881 and 1887 showed that if there was an ether, it was affecting any light by so small that it couldn't be measured by experimental equipment, or if it could, that it was falling within the margin of error.
Wrong.
Wow, you're terrible, truly a disgrace to the great nation of physics. I'm busy making physics great again while you're here being a failure, crooked ref.
This is Rashivadi from Columbia University. Welcome to Daily Physics, episode 11. Today we're going to do one of the most famous physics experiment, Michelson-Morley's interferometer. Welcome, Ref.
Thank you, Dad. Hello, folks. This is Ref.
Welcome, failure.
University physics grad student.
Welcome, Isaac.
Hello.
All right. So let's jump in. What happened in 1860?
The Civil War?
No. James Clerk Maxwell unified all four Maxwell's equations.
Who the hell cares about that, man?
That was 1865, actually. Not 1860.
That's when it ended, stupid.
Okay.
What?
That was 1865 is when the Civil War ended.
Okay.
Wait, what war?
No, we are not talking about Civil War. Okay. We are definitely not talking about Civil War. Welcome to physics. Okay. Civil War is important, but physics is also important. Let's go back to physics. Okay, so what happened 1865, James Clerk Maxwell gave us this equation and he calculated the value of this equation and it turned out to be what? 3 times?
10 to the 8.
10 to the 8 meter per second. Excellent. So everything went well except one thing. What was that?
The ether.
Yeah, he used ether.
Yeah, the hypothesis is that just like every other wave known up to that point, light will need a medium.
That's right.
Of course, it turned out in the end light doesn't need a medium, but this was the core assumption of Maxwell's theory.
In fact, okay, so that takes us like decades later, Michelson-Morley, Albert Michelson, and Morley was his lab assistant. So most of the credit goes to Albert Michelson. So what did Albert Michelson do 1887 or 97?
Yeah. He tested if light travels at the same speed in all directions. Yeah.
Isaac, what did Albert Michelson do?
There was an experiment.
Okay, I can explain it better. Okay, yeah. The ether is like a wind. You don't know which way the wind is going, but you know it's going some way.
All right, so let me...
so the test was basically to reflect light in 2 different directions.
Okay, all right.
The same path length.
All right,
and
so let
check if one was slower than the other.
Let's start with a quiz. Okay, so this is the sun, right?
Who knows that?
I think 30 kilometers a second.
67.
Well, I can check.
67,000 miles per hour, right?
Okay.
Yes, 30 kilometers a second.
Wow, really?
Yep.
Nice.
Nerd!
Okay, so this is ether. Right? So I'm going to put Earth at 3 locations and you're going to tell me what happened. This is the Earth. This is the Earth.
Is it just me or is Dad's camera a little low quality?
This is the Earth. Okay, do you see the Earth?
Yeah.
At 3 locations.
Yes.
I can give you more location, but these 3 locations can solve all the possible scenarios. And how many possible scenarios?
3.
3?
Okay. Mm-hmm. If there is an ether, and of course there is, because the year is 1887, of course there is an ether. Then what do you expect? At location 1, location 2?
Yeah, of course, we all know the ether ran away as soon as the Michelson-Morley experiment disproved it.
Hey.
Oh, shit, gotta go. And it disappeared.
Their idea came from here. If the ether is true, of course, which it is, because the year is 1887, at location 1, what happened? The Earth would speed up or slow down?
Slow down.
Or light would slow down.
At location 2, the Earth will speed up or slow down?
It wouldn't be affected.
Neither.
At location 3, Earth will speed up or slow down?
Speed up.
Very nice. Okay, now we are gonna be now creating some apparatus to do an experiment. We're gonna name it interferometer. So
like the main point of the Michelson-Morley experiment was if you put a bunch of leaves into the wind, and you throw them in one direction, you'll find that the leaves will move faster with the wind than if you throw them in the exact opposite direction of the wind.
It's just like
so the
water.
exact same way,
It
there
just
really was an ether.
That's right.
If
But
there really was an ether, then you throw the light in one direction, you throw the light in the other direction, and you observe which one is going
But
faster. And if
that
they're both
inter-
going at the same speed, bada bing, bada boom, there is no ether, just like there is no wind.
the interferometer is like 8th grade, as Shubhanu explained. I mean, you can also use the boat analogy. There is a current on the river. You can use the boat analogy to explain the same thing Isaac did. And the 8th grade student, even 5th grade student should understand interferometer. But the way our physics teacher explained them, most of the students don't understand them. So now,
well, yeah, the actual specifics of the interferometer are complicated, but
Not.
the designing principle is simple.
we're gonna make it simple. That's our job, and hopefully, by doing so, we can recruit more students for physics. Okay, so that's our goal. All right. So just like this, we're gonna create 3 scenario. Okay, Isaac, can I have you here?
Okay.
All right, Isaac. Okay.
He got distracted by the board.
So I'm gonna call a location. I'm gonna call west, which is 90 degree from north, which is 90 degree from east, and east is 90 degree from south. We all agree, right?
Mhm.
Here I have a center. I'm gonna call O. I have light. I'm gonna release light. It's a monochromatic light. What is monochromatic light? Isaac, I'm gonna ask you a bunch of questions. Please don't lose attention.
Yeah, monochromatic light is
Single
light of
color.
exactly one wavelength.
A single color. One way of creating monochromatic light is by using what?
One wavelength.
Prism.
Oh wait,
Using a laser.
by-
Using a laser.
That's right.
by using a prism to split white light into its separate wavelengths.
Right. Okay. So the light. RF. The light goes from west to O, right?
Okay.
And then it's eventually go from O to E. So far so good.
Okay.
And then another second beam goes from O to N. Is that right?
Mhm.
Okay. So one beam, this is a split. This is actually 45 degree. Why this is 45 degree tilted?
Huh?
Why this mirror is 45 degree tilted?
Oh, because it's a beam splitter. It splits the light beam into 2 perpendicular directions.
Good. So one goes from 0 to E, and we're gonna call it A. One goes from 0 to N, we're gonna call it B. So far so good.
Mhm.
0 to E, we're gonna call it L. Then E to 0, we're gonna call it what? 2L.
Is it just me or is your camera bad?
Me?
Because I can't see. Yeah, your camera is.
I think it's the Wi-Fi. I don't know. Is my camera okay?
Yeah, your camera is fine.
Let me pin myself, and then will you be able to see me?
Yeah, I think it's fine. I can see everything.
Isaac, you see it better now?
Let me pin you.
Yeah. Pin me.
Yeah, I guess I can read it. It's still low quality, but I can read it.
Okay. So if
Also, that I think your collar is
me?
yeah, I think your like suit collar. Yeah. Okay.
Okay.
Yeah, there's the bad internet symbol showing up on Dad's name tag.
No, I think I can see that. I think better now.
Oh, I
It's a
don't know
little
why.
small.
My internet
I
and
can
Isaac
see.
internet should be same quality because we are in the same house. Okay, let's go back. If 0 to E is L, and then at E, what happened? It's gonna bounce
It's
back.
reflected.
It's
Yeah.
gonna reflect it from E to 0, right?
Mm-hmm.
So
Yeah.
it's gonna be 2L, right?
Yeah.
And 0 to N is gonna reflect it from N to
Oh.
O. So it's gonna be 2L as well. Is that right?
Yep.
And
Yeah.
at S, you have a detector. Is that right?
Yeah.
Now, detector will detect what? The time it takes.
Yeah.
Coming in.
The time it takes for beam 1 and beam 2.
Mm-hmm.
All right. So if beam 1, of course, is this, and beam 1 is psi x comma t is a kx minus omega t, what would be beam 2 be?
Wait, that we can't see.
Yeah.
Okay. So beam, which beam is kx minus ot?
I cannot read this camera, bro.
No. So let's see whether I can
I
pin myself. Remove. Do you see it better now?
I have you pinned and I can barely see you. I can barely read the
Rap,
board.
you don't see me?
I see you, but it's like, oh wait, okay, now it's better. Now it's better. Let's see.
Psi of x comma
Psi
t
of
is
x.
equal to a kx minus. Hey, where's the sign?
Oh, okay. So the reflected beam is just
A sign,
plus
yeah.
omega t.
A sign,
The
yeah.
reflected. Oh, Dad, are you talking about the reflected beam?
Yes, we are talking about this is A.
So
What about B? How the B would look like? What is the phase shift?
plus pi over 2. So it'll be plus omega t.
Mm-hmm.
Okay, so what would be the phase shift? Is there any phase shift?
Wait, what? You broke up.
Oh, is there any?
Actually, at the end.
Okay, my question, my main question. Let me take you to the main question now. Which one will take
Yes.
longer? Which one will take longer?
They'll take this.
Okay.
Well,
Wait.
if
Wait.
the ether.
Wait. Let me speak.
Okay.
If there was an ether, then in whatever direction the ether was going, then if this direction and the dot product of the ether's direction with this direction was greater than the dot product of the ether's direction with this direction, it would pick this. Otherwise, it would pick that. But here's the problem. If the ether doesn't exist, then the dot product of both is 0, which makes them equal. And that would mean that both of them would unify into one light signal instead of two separate blips. And so this is what you'd expect to find if there was no ether, while this is what you'd expect to find if there was an ether. And would you look at that, Michelson and Morley found that one constructive signal instead of the two split ones.
Okay, so this we can use the. How can we use earth and sun analogy to understand this? As
Well, it's a little
Earth
flimsy.
as Earth moves around the sun, if there is an ether, what happens? We consider three scenarios.
So you
Well,
can run the. Oh, Shiva, you want to say it or?
Well,
So here's how you can do it.
that
You can run the Michelson-Morley experiment 3 times. Every time they got the same results. When the Earth was in the north or in the east or in the west, it doesn't matter where the Earth is. That means there is no ether, because if there was an ether, then sometimes the ether would speed up the light, sometimes it would slow down. But if there's no ether, then it doesn't matter where the Earth is or when you do the experiment, you'll always get the same results. So they always have the same result.
Okay.
Yeah, just testing it once says, maybe the ether still exists, but it's just too small to detect at an earthly scale. But then testing it multiple times over the orbit and seeing absolutely no discrepancy tells you, yeah, there's no way it can exist.
Okay, so before we move to our final conversation, Isaac and Raf, who wants to go fast and summarize, nicely construct the interferometer to help understand these two light beam?
I can do it, yeah. Oh, Shiva, do you want to do it? Yeah, okay.
Okay, sure. First, Isaac go and then Raf go. I'm going to remove me.
So basically, what the interferometer is taking a light beam at the beginning, splitting it into two beams that take different paths, and then seeing which one takes longer to finish the race. Because the hypothesis is that if the ether exists, one of the tracks will be harder than the other, which should be easy. But, of course, if the ether doesn't exist...
So the ether is like a friction, right?
Yeah.
Yeah.
The friction should vary. But if the ether doesn't exist, then the two light beams should finish at the exact same time. And every single time they tested it, no matter where the Earth was in its orbit or which parameters they used, the light beams always finished at the same time. Which means that the two paths, neither one is harder than the other. They would only be harder if an ether existed, and clearly an ether doesn't exist.
Okay, very nice. Now, Ref, can you do it in a very traditional way, the way the textbook does, so student understand it?
Yeah. So, okay, so the goal is we want to know if there's an ether.
Yeah.
Okay, so
And there
the
is.
question
Our hypothesis is there is an ether.
okay, yeah.
Not
So
is there an ether?
okay.
There is the ether.
Yeah. No, okay, so the question is there an ether? And the hypothesis is yes. But the experiment says no.
Oh, okay, we'll see.
So I'll show why the experiment shows no. So if there is an ether, let me draw two diagrams. One is the big picture as the Earth travels around the sun, and then one is a picture of the Michelson-Morley interferometer. I'm gonna draw that picture here in 1 second. So let's say that we draw the Earth in three different locations, like Dad did. This is north, west, and south. And let's say that the ether is going in some random direction. So the ether is like a wind going in some direction. So now when the Earth is actually let me make it even more simple. Let's say the ether is just going this way. Okay. So now when the Earth is in the north, if I send a beam of light to the right, then the ether should speed up the beam of light. On the other hand, if I send a beam of light, let's say to the left here, when the Earth is on the south, then the ether should slow down the beam of light. And on the west, if I shoot a beam of light up, then it should not be affected by the ether. So the idea is you can test if there's an ether by seeing if light is slowing down or speeding up. So how do you actually test it with an experiment? So this is the Michelson-Morley experiment. So this is a laser. It's going to shine monochromatic light. So the laser shines some light. And then you have a beam splitter. So just like Dad drew, there's a beam splitter here. And the job of the beam splitter is to chop up the light into two separate paths. This path and this path. So let's call this path A. Let's call this path B. And then at the end of both paths, there's a mirror. So there's a mirror here and there's a mirror here. So let's call this mirror 1. Let's call this mirror 2. So when the light beams hit the mirror, then they reflect from the mirror. So let me use green again. So this beam of light is going to reflect back, and this beam of light is going to reflect back. And when they reflect back, then they combine at the detector over here.
So BD
So,
arrived there exactly at same time as AC.
yeah, exactly. Now, if there was an ether, so let's say there was an ether this way to the right, the ether would not affect B or D, but it would affect A and C. It would speed up A and it would slow down C. So at the end, you would see that there's some difference in how long it takes this horizontal light to travel versus how long it takes the vertical light to travel. And you would see that difference reflected in the interference pattern. When the two beam of light,
One moment. Oh my God.
Isaac, what is the definition of interference?
Yeah. Oh, interference.
No, I'm sorry. What is the definition of interferometer?
Oh, an interferometer is something that I think measures the fringes that occur as a result of wave interference.
Okay, interferometer is another way of saying interference. is there any interference over here? If you draw 4 waves, okay? Raf, Isaac?
Oh yeah, fully constructive interference.
Fully constructive. Can you draw A, Isaac? Wave A.
Okay. Well, wave A is something like this.
Okay,
Wave
good.
B
Can
is
you draw B now? Can you draw? Okay. So what is it constructive or destructive?
Well, it's constructive because they're both fully in phase. It took them the same amount of time to reach
So
the.
is in phase. Now can you do B and D?
What's D?
Over there.
Huh?
Raf did it from meter 1.
They'll also look the same if there's no ether.
D. A, C, B, D. Okay. So A and B are the incoming waves and C and D are the reflecting waves. Well, yeah, they both look the exact same as well. C and D.
Okay, very good. So phase shift is 0.
Yeah. Oh, one thing I wanted to say is that, of course, no experiment is perfect, and the Michelson-Morley experiment wasn't either.
Wrong.
They didn't actually prove that there was no ether. They just proved that if there was an ether, it was affecting the Earth's motion, or the motion of light, by less than 0.02%, which Michelson said, well, that falls well within the margin of error, so
That's
that means
right.
there could be no ether at all.
That's right.
It looked like a failed experiment. And they've been repeating this. Wait. The first true proof that there was no ether was in the theory of relativity. But they've been repeating this experiment. The most recent experiment showed that if there is an ether, it's affecting light by less than 10 to the minus 17%. And of course, the first definite proof that the ether doesn't exist is in the theories of relativity. So this didn't actually prove that there was no ether, but it put the ether into question. And as Einstein said himself, the theory of relativity wouldn't exist if, the Michelson-Morley experiment didn't exist. Because the Michelson-Morley experiment was one of the things that put our classical model of physics into question.
So Raf, Isaac is right. It was one of the, I think, most famous failed experiment.
No, it's the most.
The most, because they failed to accept the hypothesis. So it was failed experiment and they had no idea why. They couldn't explain it. So it took more than 10 years, 1887 to 1905. So Einstein really helped us understand what's going on. Yeah, so Einstein helped us understand what's going on. So how did Einstein help us? What's going on? Number one, what did he say?
So Einstein did something amazing. He said, I'm just gonna make this.
Number one, he said there is no ether. Okay.
Yeah, he made it a postulate. So light is the same speed in all reference frames.
Okay. Because space is not absolute and time is not absolute.
No. Because it's not. He made it a postulate of special relativity. So it's something that you just assume that light is the same speed in all reference frames, and then you show that to make light the same speed in all reference frames, space cannot be absolute and time cannot be absolute. So it's the other way around.
So you need the time dilation and space length contraction
to make the speed of light the same in all reference frames. Yeah,
that's right. And so you have to adjust your time to agree with to keep the speed of light same.
Yeah, and also gravitational waves were also detected with a LIGO, which looks just like this. It's also an interferometer.
Yeah. One more weird thing I want to show you. Can I show you something? Can I share my screen?
Yeah.
Yeah. Look at this. Did you know this is Michelson?
Yeah, he worked for U.S. Navy. Yeah, he was the only person who has never been a professor.
Yeah, he was a soldier for many years.
Yes.
Really?
Yeah. Yeah, he was.
Wow.
This is straight off his Wikipedia page.
Yeah, he was a U.S. Navy, and what he did actually, he worked with optics, and this was his obsession. So in his free time in the submarine, that would be something he would be doing, and he would be reading
Oh wow!
all the
And
fascinating, cutting edge
it
research.
looks like his great nephew is actually a gamma ray researcher at Stanford University. So
Yeah, and a few years ago, I had his grandson as my student, and his name was Romeo, and
Oh,
F. Yeah,
I remember that.
grandson or great grandson?
great grandson. Yeah,
What was his name?
Romeo.
Was his last name Michelson or?
Yeah, Michelson. Romeo
Well,
Michelson.
it has
Wow.
to.
Yeah,
Wow.
it's just a pride. So they never
You really have a connection. Huh?
Wait, was he good in physics?
Yeah, he was
Can
good. He was good, but he has lots of what do you call expectation, lots of
Oh, okay. Oh,
expectation.
He has
yeah.
lots of pressure.
Makes
Pressure,
sense.
yes. You
Makes
guys have
sense.
no pressure because
Yeah.
he
Well,
has
yeah,
lots of
especially
pressure.
because that guy's uncle is already a professor at Stanford University. He
Oh,
probably
really?
hasn't seen it.
well, and Albert Michelson was the first American won the Nobel Prize in science,
Mhm.
and
Yeah,
In
so they've got
1902, yeah.
yeah,
1907, dumb. I don't know
1902.
either. No,
1902.
no, not
You should
1902.
really.
1903, I know Curie won the Nobel Prize, and 1907, I think Albert Michelson won the Nobel Prize.
Yes, I told you.
But can you check? Can you check, Isaac? What year he won
Albert
the Nobel
Michael.
Prize?
In 1907, he received the Nobel Prize in Physics, becoming the first American to win the Nobel Prize in Science.
Yeah.
Oh, so I was right.
So
No, I said 1907, dumb.
That's what I said.
So
No, you
Albert-
said 1902.
So two Albert, lots of free time. One Albert in patent office, other Albert in submarine. So in the submarine, he had lots of free time.
Oh, and the third Albert, 100 years later, is busy being a failure, unfortunately.
Hey,
All right. Okay. So summarize. First, Raf, you summarize. You have 1 minute.
okay, so the Michelson-Morley experiment found that the speed of light is independent of the reference frame. So regardless of when they did the experiment, when the Earth was in the north of the sun, south of the sun, west of the sun, they always got the same results. So that means there was no ether to slow down or speed up light in any direction.
To be more precise,
So that means the Michelson-Morley experiment was a null result. There was no ether, and Einstein used that as the postulate for his special theory of relativity. As did I for my special theory of my relativity.
That take us to Isaac. Isaac.
okay, I'm much better at summarizing things. I'm the greatest.
I'm much better than
Wow, you're terrible. Truly a disgrace to the great nation of physics. I'm busy making physics great again while you're here being a failure, crooked ref. Okay. The Michelson-Morley experiments of 1881 and 1887 showed that if there was an ether, it was affecting any light by so small that it couldn't be measured by experimental equipment, or if it could, that it was falling within the margin of error. And that experimental result, when everybody previously assumed there was an ether for light, like all other waves, and a bunch of other experiments showed there was an ether, called the standard model of physics into question. And it paved the path for Einstein to set out his special and general theories of relativity, which dictated that not only is there not an ether, but actually no matter what reference frame you're in, there is definitive proof that light speed does not change at all. And of course, this is only being verified time and time again by people replicating Morley's experiment to higher and higher sensitivities. So the essence of Michelson-Morley's experiment was just sending light on two different paths of the same length, and so seeing if either of them took longer than the other. And if neither of them took longer than the other, then that would mean that ether was not having much of a significant effect on either of the two paths for there to be a difference, and hence the ether was so small that it couldn't possibly exist.
He's wrong. If the speed of light doesn't change, why does light slow down in water?
Good goddamn question. I said it doesn't change when you change reference frames.
Wrong. So why
No
does light
matter
slow
what
down in
reference,
water?
that's a totally different question. I said if you change reference frame, no matter what reference frame you're in, if light is in water, it will be in water. That can't be changed. But no matter what reference frame you're in, light speed in water will not be different.
Right.
Are you picking up
So-
what I'm putting down?
So in the water, you know,
You're throwing a completely irrelevant question at me, and I'm debunking you and destroying you like the incompetent liberal you are.
so Raf, you agree with
Uh-huh.
him? If you are a fish and you're looking at light in the water with other fish, but from different angle, one fish would be, I don't know, in the ship, one fish would be in the, I don't know, boat, one fish would be, but they're looking at the other fish moving, but speed of light would be same, which is 3 times 10 raised to 8 divided by 1.33, right?
Yeah, Ref's got about the brain of a
So-
fish, so you perfectly suited to answer this.
So the short answer is that that's right. The light slowing down in water has nothing to do with the speed of light being the same in all reference frames. Because when light goes
Yeah, I
into
told
water,
you. You're throwing me a completely irrelevant question.
When light goes
Bogus.
from
That's
when
malarkey.
light
I'm
when
being
light goes
serious right now.
okay, when light goes from air to water, it's changing mediums. It's not changing reference frames. Changing mediums slows down light. Changing reference frames does not slow down light.
The least eloquent description of anything in physics I've ever heard. My fourth grade teacher could explain this better, and she's never even taken a physics class.
Everybody, it has been a wonderful physics discussion with Raf from Brown,
Sure.
Shivan Isaac from NYU. Please join us tomorrow.